So we are moving to unavoidable errors in computing. I will post the PowerPoint right after the class, if I have it already. And essentially, the problem of errors you have already encountered. You're consistently typing things in wrongly, okay? And then you have to look for the mistake you made while typing. Those are the ones that we call avoidable errors. Sometimes you put in an extra parentheses, or you put the wrong type of parentheses. And sometimes the computer can actually recover from what you entered because it means something else. Okay? In which case you get these really weird errors. It's running, it's executing, but you're like trying to figure out what on earth is it thinking. And sometimes it just tells you, no, can't do, you gotta go to this and this line and fix something. Okay? All those that you type in and then you fix as you type in are called avoidable errors, because technically you could have avoided. Now, there are some of them that are unavoidable, and they're due to the finite space. So for instance, number pi, we know that we can go forever with all of the digits that you can have in pi. You start with 3.14 and you keep going. And it's actually an exercise in math, figuring out what is some very distant digit in that number. However, in computer, we have finite space to fit that number in. So some of that number will have to be chopped off. And therefore, in such a way, we are introducing an error. So the error could be actually in fitting the number into a memory. So it's a finite size of memory, and the number might have infinite amount of information. And the second problem is that I might have a formula that goes, those sums in calculus that go to infinity. Well, I can't go to infinity. I gotta stop somewhere. Okay? And we do stop. And therefore, we are making an error. We have truncated the formula. Our question is really, how big is the error and do I care? Because sometimes I can't even evaluate with my measuring devices that I made an error. Therefore, because in any measurement that we make, we also have sort of an error in the measurement, right? So, to a certain extent, yes, there are errors, but some of them don't matter all that much as long as they don't pile up and bite me back. Okay? So we're going to basically learn about both the errors and how to evaluate them when we truncate formulas and chop off certain parts of the formula and make an approximation, as well as those errors of fitting and possibly infinite number into a finite memory spot, and what is the error that we make. You have probably encountered the second one already, where sometimes, curiously enough, your number instead of being 2 shows up as 2.0000001 or something of that sort. That's actually the evidence of this finite errors showing up in your numbers. So let's get going with the first one. So again, bug is sort of what we call avoidable errors. Those are the ones that we typed in and have to figure out where they were. However, some of them are not avoidable. So here's the example of the truncation error that I mentioned. So if I have a formula that sums up all of the elements of the type 1 over I as I goes from 1 to infinity, okay? This is an infinite sum. And in the reality, I'm going to go to 10,000 or so and then stop, okay? And therefore, whatever I chopped off from 10,001 onward is the error I made in this process. That's called truncation error. Okay? So I have an infinite or continuous formula in mathematics has simply been truncated. There's also a round of error, okay? And sometimes, so there are two parts to it. One is the actual number, sometimes just like that number pi, I have finite space, so some of it will either be rounded off or chopped off at the end, and that's the error that I make. Okay? But there's also, sometimes I can have a very accurately represented number and another accurately represented number, and both are actually fitting into memory and all as well. I haven't made a But then once I add them together, the result of that addition I cannot store accurately. Okay? So there is some of it that could be due to the actual computation that I do with it. Okay, so the process of adding or multiplying. And that happens a lot, and we will see why. This is something to do with the way we store real numbers in the memory. If I have numbers that are very far apart in magnitude, okay, I will have to basically chop the second part off. So this one I might be actually able to store accurately. This one I might be able to store accurately, but when I try to add them together, I can't fit the result into the memory. And we will see why. That's because of a very specific way we store real numbers. Okay. So there's part of it that happens due to the actual computation. Okay. So first we have to measure errors, and you have had an exercise of measuring errors in your homework that you just submitted. Basically, if I know the true value, I take this approximation that I made, and I look at the difference, and I take the absolute value. So that's just absolute value. More useful one is the relative error, where I actually look at it as a percentage or a fraction of the value that I'm looking for. So, for instance, here's an example. Let's say that I have bridge and a river, and that bridge is 100 centimeters wide. And let's say that I make a measurement and I estimate it's 99. Okay? I have made an absolute error of 1 centimeter in this measurement. Okay? Now, let's say that river is 1,000 centimeters wide. Okay? And I measure 999 centimeters. Okay? Again, I made an absolute error of 1 centimeter. So absolute error in both cases is the same. However, in first case, I made 1 centimeter error relative to 10. And in the second case, I made 1 centimeter error relative to 1,000. So in terms of the percentage of what I was actually measuring, I made less of what we refer to as a relative error in the second case. Okay? So in the first case, my relative error is 1%. In the second case, it's 0.1 or 0.1% or a fraction of 0.001. Does that make sense? So technically, if you want to compare different measurements against each other, okay, so sometimes bridge is 100 centimeters wide. That's a small bridge, but anyway, it's over a creek, okay? But sometimes bridges over a creek, and sometimes bridges over Colorado River, okay? And in those two cases, if I'm just wondering what is the relative error and want to compare those two cases, then I do have to look at the relative error, right? Because I don't want to look at apples and oranges together, okay? So in essence, relative error, in my personal opinion, is kind of something that I more care about. But if I'm kind of working with something that is, with things that are approximately the same size, then I can talk about absolute error that's just fine. So let's talk about a little more about truncation error. So I have already I have already made an example where I have these infinite series and sums. Okay, so often we actually represent functions as these infinite sums, and you probably don't remember, but you will recall in this section of the course Taylor series, right? Taylor or Maclaurin series that are used for evaluating a function around a certain neighborhood or a certain value. Okay? So in this particular instance, I have e to the x is actually the same as 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial and so forth. And that's how we actually compute it. Okay? Because at some point I decide how many of these elements is enough, and I stop. Okay? And I sum them up. And that's the value that your computer is when you actually say e to the x or put it in your calculator, that's the value you're getting out. Okay? So this is the example of truncation error. Another problem is, another example is having, for instance, derivatives. So often, instead of computing a derivative, if I have a function, I can compute the derivative. Right? I know how, calculus has taught me how. However, sometimes we have data. Okay? Sometimes my function, okay, is my porosity measurement in a valve. Okay? And that's a function of that. And in that case, I don't have an actual function that I can do a derivative of if I'm looking at the changes in these porosities. I need to compute it from data. And from data, I will take two neighboring points, probably 0.5 foot or 1 foot apart, and I'm going to look at the difference and divide by that 1 foot of difference. That's my approximation to the derivative. So we know that basically derivative, or definition of a derivative for a function f, is actually something looking like this: f of xi plus 1 minus f of xi divided by xi plus 1 minus xi. And we take a limit of this as xi plus 1 approaches xi, right? I kind of shrink that difference, right? So therefore, I can take two values like this and approximate my derivative locally just by what this is called a finite difference. Okay? So I take two neighboring points, xi f of xi, and xi plus 1 f of xi plus 1. Those are two neighboring points on a graph. And I just look at the differences in values divided by differences of those values. That's essentially the slope of my graph. And that's an approximation. So I can also then look like what is the error I'm making by using that type of approximation. So that's another example of a mathematical formula that is approximate, so you can look at the errors. So Taylor series, just to remind you, I hope this is not too shocking of a calculus formula, but essentially the way we do Taylor series for any function, I'm looking to basically look at the polynomial expression that approximates the function in a vicinity of a point x0. So in that vicinity, I will approximate for any value x in that neighborhood. I'm going to say, well, it's the value of the function at f of x0 plus the difference between the 2 points times the first order derivative of f evaluated at x is equal to x0 plus the second, so basically x minus x0 squared divided by 2 factorial times the second order derivative. And if my function is nice and differentiable and continuously differentiable and so forth, as long as I keep going, I can keep going. So that e to the x that I showed you, that series, is actually this Taylor formula applied around x0 is equal to 0. Okay? And every derivative of e to the x is e to the x. Okay? So you can actually plug in derivatives as we go along and get that series. So basically for every function, what I'm looking at here, these are some numbers. This is a derivative of a function evaluated at a specific point. So it's actually a number, a constant. Sorry. So this is essentially a polynomial. Okay? And then there is this rest of it is this reminder. And this is when I decide to chop off my series somewhere. This is the error I'm making. This is what I chopped off. And Taylor's formulas actually give me an estimate on that error. So I can actually go and find out what that is. Now, we will again have just examples, and I will do this example at the end. I will let you, keep 1 term or 2 terms or 3 terms in this formula, and we will evaluate the error we are making in that process so that you get the sense of what this approximation does to the error. Okay. Now, when we have an iteration and we are actually arriving at a solution to a problem by doing my for loop or a while loop or whatever was applicable, again, in homework, that was that square root function. Okay. So often, you can evaluate the exact error against a true solution if you have that true solution. But often we just have to keep going until the solutions we're getting are simply close enough. and we evaluate how these, in 2 iterations, neighboring iterations, I get 2 values. I kind of evaluate how close they are. And at some point I decide these are 2 close enough, they're 0.0001 apart, that's close enough for me, I'm going to stop. So whenever we develop algorithms that kind of iterate toward my solution, we stop when my solutions in 2 steps get very close. Because I'm kind of converging, I'm zooming in on a solution, and I'm thinking that should be fine. So we are the ones who decide what is this delta or epsilon or however we call this cutoff number, when my difference in absolute value between 2 iterations, we call them x old and x new in homework. Okay? When the difference between 2 is small enough, we say enough, we're good. Okay? And that's how we stop in algorithms. Okay? So that's something. So we have some small tolerance. Okay? Ideally, I would like to actually evaluate my guess against an actual solution, but if I don't have actual solution, I'm looking for it, okay? Then I have to stop when 2 neighboring iterates are. So that's a practical map. So sometimes we will test, like sometimes you write an algorithm and you test it against the case that you know. Okay? So in terms of testing square root, you know that square root of 4 is 2. So that's your testing problem. Okay? And in that case, you actually know the actual solution. But then if I ask you, hey, give me square root of 2.5, or 4.5, right? I don't necessarily have that value, so I can test my algorithm in that case only by looking at the 2 neighboring values in my iteration process. Okay? And that's when I stop. And I then trust my numerical algorithm, even though I tested it only in a few cases where I know the solution. That's simply the reality of numerical computing. So let's do an exercise. So that, like, I blabbed a lot. Let's see whether I sent a lot of information. Let's see if it was received. So let's do this example case. I have a function, a known function, 1 over x plus 1. Okay? And I'm interested in looking at values of that function around x0 is equal to 1 using Taylor series. So I want to evaluate f of 3 and f of 2 using 1, 2, and 3 terms in my Taylor series. And I want to see how accurate that is. Good news is that for this function, right, I actually can evaluate that function. I know the function. But I want to see how good is Taylor series. So what I'd like you to do is basically have a little spreadsheet, so something like this. So I basically want you to insert table. So something like this. I want you to compute f of 2 approximation. And this is f. And f of 3 approximation. Using 1 term in Taylor series, using 2 terms, using 3 terms. And this approximation is around 0.1. So basically my f of x, again, is this. So in this case, using just 1 term, right? This is simply f of 1 that I can type in immediately, which is 1 divided by 1 plus 1.
So that's 0.5. And that's the same case here. So now if I add plus, in this case, 2 minus 1 times derivative of f evaluated at 1, f prime of 1, I'm wondering what's going to happen here versus what's going to happen for 3. So use this Taylor formula that is here on the slide to fill this in. What is f prime of x when f of x is 1 over x plus 1? That would be integral. Don't integrate. Differentiate. Okay. It's going in the right direction, just change it. 180 degrees on the other side. Okay? If I do it once again, what do I get? 2. So that's what you're using in this partial f partial x evaluated at x. And your x0 is 1. So did anybody get f of 2 using 2 terms? It's obviously this term, which is 0.5, plus 2 minus 1, so that's 2 minus 1 is 1, times f prime of 1. What is f prime of 1? F prime of 1 is minus 1 over 2 squared. Anybody? I don't see any. I'm just saying, like, yes? This is a f prime of x0. My x0 is 1. Putting things into formula. Yes? Maybe? Maybe. Okay, there's somebody. Okay, so this is minus 1 over minus 1 over 4, right? Which is minus 0.25. So this is 0.25. Yeah? Can you do this second one the same way? What do I get? No, it's still 4.
Do we agree? Did I do this right? And then if I want to add this term,
It's whatever I computed using 2 terms, so I'm just going to use that number, plus 2 minus 1 squared is still 1, divided by 2 factorial, that's 1 over 2, times f double prime
at 1, and that's 2 over 8. Yes?
Okay, so if you're using 2 terms for your F3 approximation, why is it negative 1/4 instead of positive 1/9?
Because I have to evaluate double prime at 1, not at 3 or 2. So this is at x is equal to x0, which is 1. So this is f prime of 1 in both cases. Right? What changes is this difference here. Right? So in the first case, I'm doing 2 minus 1 times f prime of 1, and in the second case, I'm doing 3 minus 1 times f prime of 1. F prime of 1 in both cases is the same. It's minus 1 over 2 squared. Yes?
Important to differentiate because you would kind of automatically try to change it, but it's actually this number is the same. This number is the same regardless of whether you're evaluating f of 2 or f of 3. This number. Okay? This number changes. Yes? So that's what I mean is that it's technically constant for this given value of x0. So this is going to be, where am I? Again, this is f double prime of x0, which is 2 over 8, which is 1 over 4. So 1 over 4 times 1 over 2 is 1 over 8, so that's 0.125, so this is 0.365.
And in second case,
I have 0, which is this previous sum, plus 2 squared, which is 4 divided by 2, also times the same number here. Okay. So that's 2 times 1 over 4, so that's 1.5, so it's 0.5. Are we okay with the process? Any questions? So it's looking closely at the formula and applying it correctly, which takes a little bit of practice. Now, great, so my f of 2, as I'm adding terms, obviously initially I'm estimating both f of 2 and f of 3 to be 0.5. That's bad. Okay, that's approximation with a constant. So that's poor approximation. I would expect that. Then with adding the second term, I seem to be changing values, but I don't know whether I'm getting better or getting worse. Okay. Partly because I need the actual value.
to actually evaluate that. My actual value, luckily I know what is actual value for f of 2. I actually know the function.
What is actual value? 1 divided by 2 plus 1, right? So that's 1/3. 0.3333 and so forth.
Shouldn't that be 0.375?
So point no.
Yeah, for using 3 terms of 2.
1/4 times a half is an 8.
7.5, yes, thank you. Oh, that was a test. Thank you. So, I seem to be, it's 0.5 and 0.25, and I have this plus minus in the formula, but it seems that I'm getting closer to 0.3333, yes? So if I add more terms, I will get more accurate. The second term though, I'm actually pretty far away. Taylor series works when you're close to the point x0. 3 is pretty far away for this function anyway. So in this case, it seems that I'm at 0.5, 0, 0.5, and maybe next one is again 0, so I'm actually never converging. So it's actually a good question whether I'm converging to the value. And the value that is actually actual value is 1 divided by 3 plus 1, which is 0.25. So based on this case, I don't actually even know whether I'm converging. Okay. What is the absolute error in the case of f of 2 using 3 terms?
In this case. So my absolute value is absolute value of 0.375 minus 1/3, right? So that's 0.042 and so forth. Approximately. I'm rounding up.
Yes? What is the relative error?
It's that same absolute value divided by the actual value or absolute value of it, so 1/3.
So it's a little over 10%. Somebody has calculated for me. You can ask Google what is 0.042 divided by 0.333.
0.126. So 12.6% or so. Okay?
Questions? So again, I have an approximate formula. I truncate it somewhere. Based on how much I truncate it, I get a better or worse result. And the way I measure how good or bad is that result is by calculating absolute error and relative error.
You could do a similar example with
Finite difference. Okay. So let's do that one as well.
and I'm actually gonna go and use Jupyter Notebook as my calculator, because why not? So my question here is, how accurate is approximation for the finite difference derivative at, again, x0 is 1, using x1 1.01 and x1 1.001? And finite difference formula, so in this case I'm just going to place this as an x0. It's f of x1 minus f of x0 divided by the difference between the two. Okay, so that's my approximation of the derivative. So first, let's define ourselves a function, f, that returns 1 over x plus 1. How do I do that in Python? I want to define a function that, what do I start with? I could, do I need NumPy for that? NumPy for that? Sure, I can. It doesn't hurt. Ain't gonna hurt. You can just write that down and ain't gonna hurt you. But in this case, so I want function, so I do def to define the function. I'm gonna name it f, why not? Of x, and then my colon has to be there that I love forgetting. And what am I going to return? Yes? That's it. So if I'm just interested in this for like single value x, I don't need NumPy. If I want this to work for an entire array, I need NumPy. Did we catch the difference? Because NumPy can actually handle arrays and dividing element by element within an array. But that's aside. Okay, this is my function. Now that it's defined, I'm wondering, how do I get this finite difference? So the finite difference, I'm going to say dfx. So first I'm going to define myself as x0 is 1. And my x1 is 1.01. So my finite difference, I'm going to call it dfx. I have to call it somehow. dfx is basically f of x1, and I have defined myself a function f. So Python knows what I'm talking about, hopefully. Minus f of x0, all of that in brackets, and if divided by difference between the two. Yeah, so I'm just using Python as a calculator really. Let's see if I had any typos. No. So I can print dfx and I get a value. What is my actual value? df true. What is my true value? Of the derivative for this particular function. It's analytically defined. Yes? Great? So I could actually program that as a, well, why not? df of x return minus 1 divided by x plus 1 squared. So my true value is df of x0. And I'm going to print or do error calculation Now that NP, thank you for importing NP. It's coming in handy. NP.absolute value. So let's see what the error is. My error is pretty good, right? So it's basically, if I multiply that by 100, it's 0.12%. How does it change if I do 1.001? This is the beauty of computing. If I did this by hand, I would have to recalculate. Here, I just throw in another 0 in there. So let's see how does it change. So here it's 0.0012 compared to 10 times less. Yes, as I get closer. So typically my errors get better when I'm closer, when points are closer together. Okay? All right. So including this, okay, is on the exam. One more question for you. So on Friday, I am busy